This topic of angular measure is presenting us with some quantities that are going to be useful for describing circular motion as well as rotational motion, which include things like rolling objects in addition. So, like a wheel rolling along the ground in particular without slipping, some of these formulas will be useful for that as well. The first formula here is one that's maybe a little bit familiar. The S is equal to r theta is the arc length formula. I've drawn a picture up here to kind of remind us what the different parts are. So if we're thinking about like part of a circle, you could call this a sector of a circle, but maybe it's like a pie slice, right, out of a circle that has two line segments with length r for the radius. S is the arc length, and angle is theta here. And again, they relate by S is equal to r times theta. It's very important to recognize, though, that theta has to be in radians, and I always find it helpful to consider this equation in together with like the circumference formula 2 pi r and recognize, well, for a whole circle theta would be 2 pi and then s would be the circumference, and so this is really just like the formula that works if it's not a whole circle, and that makes a lot of conceptual sense to me at least. The second formula we have here is a definition of the angular speed slash velocity. I'm saying speed slash velocity because if somebody said, well, which one is it? My answer is it could be both. As with regular, good old linear or whatever speed and velocity, the key difference is velocity has direction and speed doesn't, and the magnitude of velocity is the speed, and that pretty much holds true for these angular based quantities here. And the thing you can see from the definition is it's a delta theta over a delta t. So it's really like a change in angle per time. And in that sense, if you said like, well, what's the units of it? Maybe it's a radian per second, provided that theta is in radians. And we're generally going to be working on under the assumption that for this stuff, we're going to be working under the assumption that the angle is in radians. You know, a question that sometimes comes up because we have done problems already in this class where it's been a-okay to keep angles in degrees. And so the question is like, how do I know when do I need to do radians? I know back in the day I took a trigonometry class and the rule pretty much was always radians, but again, that hasn't been the rule for this class. My general rule is if you have something that's an angle, like symbolized by maybe a theta or whatever other symbol is common for describing an angle, if it's inside a trigonometry function, you can pretty much choose. Do you want to work in degrees? Do you want to work in radians? And the most important thing is to make sure that whatever calculating device you use is in the correct mode when you apply that function to an angular quantity. If it's outside a trig function, as these thetas here, the ones that occur in both of these equations both are, then the general rule is that you have to use radians. And the reason why is that if you didn't use radians, these formulas would actually have to change to reflect that. In that sense, going from radians to degrees is more than just a conversion of units, but actually kind of redefines what an angle is in a way that's like, you know, a little bit more non-trivial, you could say, or less trivial, I guess, than saying, oh, I'm going to use centimeters versus meters or feet versus inches or whatever. So one of the issues that we're not going to deal with too much in this topic is, since angular speed slash velocity could be a velocity, well, how do you ascribe a direction to it? I'm just going to mention for the curious, like if you have an object, like this might be an object just rotating here, or maybe there's some point-like object that's moving in a circle but in this kind of counterclockwise direction. And I've put the statement here that in this case the direction is out of the board. What I mean by that is the direction of omega, which represents the angular velocity, is out of the board. And there's a general rule in physics that I don't know if I can show you very easily in this format, but there's a right hand rule that if you take the fingers of your right hand and you curl them in the direction that these arrows indicate, then your thumb points outward, out of the board, back like towards you if you're viewing this. One way to symbolize that, like as a symbol, is like if I write omega here, and maybe I'll put a vector symbol over this to be clear, since if it really is an angular velocity, it should be a vector, although again for pictures it's kind of optional. But one way to symbolize that out of the boardness of it, if you will, is to draw a little dot with a circle out of it, and that indicates it's coming out of the board. If you're curious what the symbol is for going like into the board, it's just a little X, and the history of that is this looks like an arrow coming towards you, and the one for going into the board looks like the fletch of an arrow going away from you. So those will be two symbols, and we'll use the other one, I'm sure, at some point in the future. But I just wanted to have this one example up here, and if you practice it on your own with your right hand just to see how it works, that may be useful. We're going to look at that a little bit more in some future chapters where we go into like rotation and torque and that kind of stuff, where this stuff becomes more important. In this chapter, it's maybe not quite so crucial yet, but I'm just mentioning it. The last formula we have here is V is equal to R omega, and this is essentially a formula that lets you go between angular speed or velocity to ordinary speed or velocity. I said ordinary there, but really the comment I've put over here is that it works for tangential velocity. In that sense, like going back to this picture of a rotating object, if I said, what's the tangential velocity there, or tangential speed if you like, if I took some point right at the edge of it and I said, well, what's the speed there? That could be what this V represents. But it turns out it also works for a linear velocity. If this represents an object, say, rolling over the ground, so if there was some ground it was on, like horizontal ground or whatever, I guess it doesn't have to be horizontal, this thing I think looks like it would be kind of rolling leftwise. And if it doesn't slip, that tangential velocity is actually going to be exactly equal in magnitude to the linear velocity of the rolling object. So in that sense, I'm mentioning you can apply this formula in multiple types of situations, and we will see that in an example or two. And rolling objects are among those. The key issue is it needs to be without slipping. If it is slipping, this relationship will not wind up holding.